Okay, next we have a very similar setup as you can see in the figure. Current is going down, magnetic field is into the page, and we have that strip. But this time the charge carriers are positive, and if you look at the top previous case, we had the negative charge carriers like electrons, right? And we found out that we had high potential on the left side. This is high potential, and this is low potential on the right side. And then the electric field goes from left to right. Again, the current direction is not different. It's just that we are saying this was the negative charge carriers were going that way, and now we are saying the positive charge carriers going that way, and we'll see how different we're going to get the answers. So again, the wire is submerged in a B field, the moving charges feel a force, but we have positive charge carriers. And let's think about this again. This time the velocity, the motion direction is downward, right? V cross B. When you do this, you're going to use your right hand, and let's just draw 4 fingers and the thumb. Again, 4 fingers along the velocity direction, right? And the magnetic field is into the page, so this is the top of your hand, and the force is pointing that way. And since this is a positive charge, this is going to be the magnetic force, because V cross B direction is exactly the same as force direction for a positive charge, right? So this means the magnetic force will push the positive charges on the right side, which is different than the previous case, okay? And that means we will have negatives on the left side. Let's just look at the upper picture. You can see the high low, and now it becomes low high. So this side is low potential, this side is high potential. So what this really mean, because we didn't change the current direction, but depending on what type of charge carriers move, the Hall effect can tell you that. Was it the negative charge carriers were moving or the positive charge carriers moving? Because you will see the potential difference oppositely on each side, right? So like the sign wise, like if you go from left to right, one will be positive, the other one will be negative. So in this case, the positive charges are pushed to the right, not the negative charges, like before. And potential is on the left side, is lower on the left side, not on the right side. Okay, so Hall effect tells us the sign of the charge carriers and also the density of charge carriers. Okay, and similar setup gives us different potential differences. You can see like the different low and high potential sides, but they are always perpendicular to the current direction. The charge carriers go along the current direction or opposite, depending on whether they are positive charge carriers or negative charge carriers. Okay, so let's take some notes here, the Hall effect, and let's look at the what happens. Let's get some equations put in here. So once the charges are in equilibrium, as I think I skipped that part here. So when we have that magnetic force, the charges are feeling a push, right? In this case, positive charge is being pushed to the right side like that. So that's why we said the magnetic force is to the right. And then this is going to create an electric field. In this case, the E field is going to be from left to right. And the force on this charge due to electric field is going to be also along the electric field, because this charge is positive. So when do we reach an equilibrium? Remember, this force of electric field is something that builds up. You're starting with the magnetic force, and because of those charges are moving due to the magnetic force, you're building up the potential difference. That potential difference is creating an electric field, which building up as well. And then it's gonna have an electric force because there's a charge in there, and that charge will feel that electric force as well, but that is also increasing due to V, the potential difference, and also the electric field increasing. Okay, the distance D is not changing, right? But E and V are changing. So when do we reach electrostatic? When do we reach an equilibrium? Okay, the charges are still moving, but they will reach an equilibrium when the electric field force will be equal to magnetic field force, because it's going to reach a point that magnetic force is the same as electric field force, and you're not changing the magnetic force, and there's no more motion, right? They are the same, so it's not being pushed to the right or left. In this case, it was to the right. The positive charge carriers were pushed to the right. Instead, it's going to just go straight, okay? But because we have both of those forces against each other, so that means when the magnitudes are the same but they're opposite, we will reach an equilibrium. And so the charges are going to go kind of undeflected. And if you write the magnitudes of each, Q times E is Fe, Q, VB, and sine theta, but I'm just going to write sine 90 here because V and B are perpendicular, right? That angle is 90. Then from this, you can also see that charges, it's the same charge, it's going to go away, so the velocity is E over B. This equation, I do not want you to memorize it, although it's a simple equation. I want you to start from here, okay? Understand the physics behind. There's going to be an equilibrium reached. And in the case we have the electric force equal to magnetic force, then we will get that velocity. And then you can do a couple other things here. You can say the electric field is in potential. So I do the speed or the velocity like curly V. I'm going to make that V a little bit more. This is the potential. Okay, so we know that electric field is potential difference over D. And then V becomes potential difference V. So that's the capital V divided by B times D. So this is the speed. This is the potential difference. Okay, it's actually delta V, right? And you can also, let's see, let's put it down here. We also know that the current density is NE, right? So we're going to put a Q for that. Q being the, again, the charge, and VD, V sub D, that's the drift velocity, if you remember. And then this becomes, we already know that charge density is current over cross-sectional area. And again, that's equal to NQ VD. So we're putting what we learned from chapter 26. And VD is, if you pull that from here, we have, which is the same thing as V in our equation, that's speed. And that's equal to current divided by NQA, right? So now I'm going to write it here. The charge carrier density is, again, we use NQA, I over NQA, and that's equal to, since this was the speed, right? So we said that this was that speed from here, and that means that's going to be equal to also the voltage. Let me just try to do it a little better. Divided by BT. Okay, so from this you can find the charge carrier density, which is N, and that is magnetic field B, magnitude of that, the current, the width of the strip, this length D is the length which is perpendicular to the current direction. Okay, and then we have that voltage times the charge times the cross-sectional area, and remember this is per meters cubed because that is the density, charge carrier density, right? And that means, again, the Hall effect tells us the sign of the charge carrier, right? Because we saw that if you had for the same setup, current was down. If that was the negative charge carriers, then you have high potential on the left side and low potential on the right side. Nothing else is different. And here we said that if you have positive charge carriers, then they switch because we have now left side being low potential and right side being high potential. So it tells us what type of charge carriers are, but also the density of charge carriers. So I'm going to write that down here. Hall effect tells us the sign of the charge carrier, but also the density of charge carriers. Okay, so this little n is the charge density of the charge carriers.